This is the explanation for homework 4, question 8. We're asked to imagine a subway car that's driving around a circle. And in the subway car, there's a stone hanging from the ceiling. So we're going to draw the view of the subway car from the rear. And we kind of know intuitively, and anybody who's ridden a subway knows that as you turn to the left, things appear to shift to the right. We'll explore in a moment a little more of why that is, but what we know here is that this stone hanging from the ceiling would appear to swing to the right at some angle from the vertical. We know that if we're going around a circular curve, our acceleration is v squared over r inward. Now, why must the ball swing to the right? Conversely, why do you feel yourself pushed to the right in a subway car? Well, there's no force pushing you to the right, right? If we draw a force diagram for this, which we will, the only forces on it are gravity and tension. Imagine if you're in a subway car, turning to the left, no objects in that subway car will move to the left unless a force pushes on them. So our stone hanging from the ceiling, let's think about what would happen as this way is going to be, I'm going to do a stop motion diagram in increasing time. So if this accelerates to the left, and I have a stone hanging from the ceiling. Oh, I don't want to draw it there. You'll see what I want to do in a minute. I have a stone hanging from the ceiling. As this point of attachment shifts to the left, in the beginning the stone will stay in the same place. It's not going to accelerate unless a force acts on it. But the point of attachment has moved over here. And now, after that has happened, now that the ceiling has moved but the stone has not, now the tension force goes in this direction. And there's a horizontal component of the tension force here that begins to accelerate the ball to the left. And then it's going to stay like this. So why does the ball appear to swing to the right? Well, I don't need that one. The subway car is moving straight ahead, and then the subway car turns to the left. As it turns to the left, the ball needs a force to the left as well, because without such a force, it would just continue straight ahead. Once this tension force is diagonal, it will now have a leftward component, which I'll label here, label Tx, bringing it to the left and making it accelerate along with the car. So now let's draw the force diagram. The only forces acting on us are tension and gravity. Acceleration is not a force, velocity is not a force, inertia is not a force, centrifugal force is not a force, centripetal force is not a force. The only forces we have are real physical pushes and pulls. Let's label our components here. So this is Tx, which is T cosine theta. This one's Ty, which is T sine theta, because the angle that I'm thinking about here is the angle with the vertical. So that one. Again, this one here is the force that makes it accelerate inward. No forces go to the right. So now let's draw write Newton's laws. I'm going to choose a coordinate system so that this way is positive y, and this way is positive x. That's the direction the forces go, that's the direction the acceleration goes, and that keeps everything nice and positive. In the x direction, let's see, the only force I've got is the x component of tension. So T cosine theta equals max, which is mv squared over r. I know if I am going in a circle, my acceleration is v squared over r toward the middle. In the y direction, T sine theta minus mg equals may, which is 0, because the thing doesn't go up and down. So, doing a little algebra, this means T sine theta equals mg. So T is mg over sine theta. Whoops. Oh, I've messed up my sines and cosines. So many of you, I've been doing this for a while. Many of you, I'm very tired. Many of you have probably been looking at me this whole time and saying, Walter, your trigonometry is backwards. I did the stupid thing, right? The stupid thing of not actually thinking about the triangle and saying, oh, the x one is cosine. So let me fix my trig. X should be sine. I'm not going to re-record for this because I want to make sure I get you as many videos as I can today. So I'm just going to switch all of my trigonometry around. X should be sine, y should be cosine, this is cosine, this is cosine. Right. So now we take this equation, and we're going to substitute in for t. So I have mg over cosine theta times sine theta equals mv squared over r. Notice that I don't know the mass, but it doesn't matter. Often, if you don't know a mass, just leave it as m. It'll cancel. So right away, I can get rid of my masses. And I notice that sine over cosine is tangent. So I have g tangent theta equals v squared over r. Now the question asks us to find the radius of the curve given the velocity and the angle. So let's just solve that for r. This is r equals v squared over g tangent theta. And I'm going to go back to my laptop. I'm going to wipe the chalk dust off of my hands so I don't break it. And then I'm going to do some Google calculator work to find this. So we want 60 kilometers per hour squared divided by the quantity 10 meters per second squared times the tangent of 15 degrees. And that gives us 104 meters. critical thing about this question, the big takeaway, right, and there will be something like this on the exam, is that no force pushes this ball to the right. Yes, if you are in the car, right, if you are standing here, you would see this move over here. But really what's happening is that you and your subway car and the place on the ceiling where the rope attaches, everything else is accelerating to the left. And for the rock to go to the left as well, some force has got to pull it to the left. So the x component of tension is the force pulls it not to the right, but inward, to the left, to the inside of the curve. No force pushes this to the right. Instead, you and everything else in the subway car watching this are accelerating to the left.